here in draft physics video. Sorry if the fan noise is obnoxious, but it's really hot in here. Anyway, last of the warm days, but it's been nice. Very warm September. Anyway, so this is in the series of Professor Lewin lectures. And this isn't personal. I just happen to be watching this series of lectures, and so these are the ones I'm finding, something wrong with. But this particular part really was, I think, really egregious. I mean, this wasn't just a mistake. This is, this is chicanery, and I don't like to make that accusation, but it's just so obvious, not true what he's implying. So anyway, this has to do with the double slit interference pattern. I didn't see interferometers in this lecture anyway, but it doesn't matter. But what we're talking about now is radar. And he's going to create two sources of radar that would duplicate the double slit. And, shoot the radar. And he's arguing that somehow these two beams of radar are going to interfere with each other and create dead spots in the radar. And that's clearly what's implied. He's using the math from the double slit to justify this. He's talking about the small angle approximation here, the common things to interference math. And this doesn't have anything to do with interference. This radar signals do not interfere with each other. And he's going to do a demonstration, and the demonstration is a rig. If he did the demonstration the way it should be done, the results wouldn't be what he's implying. And it's just that simple. The radar isn't going to create no signal. That's not going to happen. No radar. So anyway, let's play some of this and proceed. Now, raise the volume.
So these are approximations which hold for small angles. And so if now we look at a 10 gigahertz transmitter, that means we have two transmitters. One here and one here. And their separation D is 23 centimeters. You see them here.
So that's the famous D in the interference equation, where they take the distance between the things rather than the width of the slits, more, well, I mean, just a glaring flaw in most two-slit math.
There. Here's one and here's the other, 23 centimeters apart. At 10 gigahertz, the wavelength is 3 centimeters.
All right, now the importance, 3 centimeters is small distance. So the issue is going to be, is a phase argument, and it's not going to be the phase of the radar that's going to be the problem. But so that 3 centimeters, the important thing to think about in terms of it's at a location somewhere else. So when you're shooting the radar and you're going to listen for it at some other location, these parallel lines end up converging, so to speak. So in effect they're converging lines even though they're considered parallel. So to this point, so here's the two emitters, and the 3 centimeter difference means when this length is 3 centimeters longer, that means the two waves are now out of phase. So when they start in phase, that is the high parts of both the waves, if we're going to use wave theory, is the same. So the waves are in phase, and because one of them is now going to be, at this point it would be 3 centimeter difference, let's say 16 inches away from the center, let's say, that just means that the two waves now will be opposite phase. So the highs will be, they'll have a zero and then a double high, so to speak, a double big. But it's really a 4 times big, but anyway, we'll go into that later. So that's what's being calculated, but that only has to do with this distance. See, there's no need for interference. There's no need for two waves interfering with each other, the classic, you know, two waves. Boy, jeez, Science Lee guy draws so well, I draw so poorly. Yet I'm some kind of artist at times. Funny. Anyway, so none of this stuff is happening. There's no interference that's creating the problem. The problem is just a distance problem. The receiver is going to be closer to one than it is to the other, and he's going to put the signals out of phase by putting a carrier tone on them. So instead of just, well, we'll get to it.
You can confirm that. Speed is speed of light. And lambda is the speed of light divided by frequency. That gives you the wavelength. And we have here at a distance L, which is 120 centimeters, we have here a receiver and a track. So this is x equals 0, and here we can move it along x.
Alright, so this is the classic two-slit diagram, except this will have nothing to do with two interference patterns. This is just going to have to do with the fact that you're moving a receiver and you're creating a longer distance for one of the two things, which you're now going to force to be out of phase because of a carrier tone.
And so you can calculate now at what angles, seen from this point, there will be a maximum there. Theta 0 is obvious. Right here there will be a maximum. The two waves, the distance between them is 0. R2 minus R1 is 0. So they will constructively interfere.
Yeah, there won't be any interference whatsoever. The two radar waves will not interfere. There will be just a signal of radar. So if he did this experiment honestly, what would happen is the detector would move and it would sense exactly the same amount of radar going both directions. It would never go to nothing. There would always be a radar signal. It obviously would get weaker as you move longer distances from the radar. So it would be at its strongest here, and it would get a little bit weaker over here, but just a little bit. But there'd be no spot where there was no radar signal. That wouldn't happen, because the radar signals are not going to interfere with each other. It's just wrong to imply they do, because they don't. This isn't a two-slit experiment. There's no slit, there's no Huygens, there's no way that this can happen. This is like saying if I shine two flashlights and I look at them from certain locations, both the flashlights go out. That never happens, and it doesn't happen to radar.
But there is another angle, theta 1, for which again there will be constructive interference. And you can confirm that I found for these numbers that theta 1 is about 7.5 degrees. This is now for maxima, and so roughly at an angle which is half that value, you will find silence. Silence means that the two radar waves will kill each other.
Okay, now you just heard that. The two radar waves will kill each other. That doesn't happen. It's a horrible misrepresentation. That doesn't happen in this experiment. The two radar signals will not cancel out. That's just not true. And he's going to get to the shenanigans. Okay, this is the shenanigans.
Essential for the maximum to be here is, of course, that the two transmitters are in phase. We could have rigged it up so that they're 180 degrees out of phase, in which case there would be silence here. Silence in this case means that the radar would kill the radar. But I do use the word science for a good reason, because the way we rig this up is...
Okay, he said rig this up, okay? It is a rig. It is nonsense. It's, like I said, he said the two radar signals will interfere. They're not going to interfere. The only thing that's going to happen is the carrier signal he's going to put on top of the radar is going to cancel out the signal. One of the two radars are saying, say a word, and because the word is a wave, it means that when it's at the peak, it's audible. When it's at the trough, it means it's opposite of audible, so to speak, negative. And so what's going to happen is that audible word and the negative signal are both going to go to the same spot, and you're going to get no word. You know, so it's like a plus and a minus will create a 0. And I'll get to that too, because that's in here. So all the components, he's certainly revealing that he knows the underlying mechanism here, that this is, and he's not acknowledging that, and instead saying things that just aren't true, that radar signals interfere with each other, and they don't.
The same way we did it before, we modulate this 10 gigahertz signal with a 1000 hertz audio signal.
Right. So instead of just using a detector, he did it before. So like I said, this is a familiar gimmick. Instead of, you know, you have two choices. You're going to detect something. You can detect the thing, the actual thing being produced, like a light. So somebody could turn on the flashlight, and I could say, well, I'm just going to detect light. And then the person could say, no, I'm going to send a signal, you know, of a certain frequency of light. Okay, and then you can detect that frequency. See, this is going a step deeper that would be totally unnecessary. There's absolutely no reason to use a carrier signal on the radar, because you can make the radar receiver just go beep every time it sees radar. Or it could turn a little light on. The little light could go on. He's used lights before, light bulbs to detect radio waves. He could just have the radar light up when it's getting a signal, and they get weaker as the signal gets weaker. But instead he used a carrier tone, which makes this a sound experiment, not a radar experiment. This makes it makes it a sound experiment rather than a electromagnetic radiation experiment. This isn't about radar. This is about a sound signal and how it gets out of phase when the carriers, okay, are different distances.
Call it amplitude modulation. And the receiver, which is here, receives the 10 gigahertz radiation, which is modulated at 1000 hertz. We feed it to an amplifier, we demodulate it, and you will hear the 1000 hertz.
Right, and so that process is just putting a signal on the signal. It's like I said, it's like me having a blinking light. And so I had, instead of a steady light. And then you saying, okay, I'm only going to detect blinking lights. And so when the blinking lights get out of phase, you know, then I'm not going to be able to see them because they're not blinking at the right frequency. And only when they're in phase will I see the right frequency. So you can sort of understand, if I have two things producing blinking, you know, two things are blinking, and they're not blinking in the same phase, all right, then I'm going to see a different frequency of signal. So if I'm looking for 1 gigahertz or 1 megahertz signal, and the two are out of phase, then I'm going to see much more frequency, and I'm not going to detect it. So the same thing is happening here. He's putting a sound wave on the radar wave, and that sound wave will have its phase broken every 3 centimeters, and in terms of there'll be half off phase, and that's what's destroying the signal, the audio signal. It's not destroying the radar signal. The radar signal's coming in perfectly clear. It's that the two audio signals are now out of phase, and they cancel each other out because they're plus and minus signals. That means it's 5 volts negative plus 5 volts positive, and that gives you a 0. That's what's canceling out, is an electrical signal, not anything to do with the radar.
And so we can also move it along this track here and find the location x1, whereby we have our first maximum apart from the 0, and I found that that is very roughly at 15.6 centimeters. And you should confirm that using those equations. The equations are the same.
Right, and I'm just saying that this whole thing is implying that that's the same kind of maxima that's seen in the double slit experiment, when it has nothing to do with the divergence in the light created by the double slit experiment, the diffraction pattern, the interference pattern. This has nothing to do with that, in the sense that the fundamental carrier signal, the radar, isn't being interfered with at all. The true electromagnetic signal, this is not two-slit interference. There's no two slits, there's no Huygens, there's no even mechanism to create the diverging signals.
You deal with sound, or with red laser light, or with gigahertz. Makes no difference.
So you just said makes no difference, makes a huge difference.
And so let's turn now to this demonstration. I will turn on the two transmitters, and here's the receiver, which is exactly at angle theta 0, so there's a maximum.
Okay, so just understand, he's got audio on top of this radar signal. So this isn't detecting the radar signal alone. It's detecting the radar plus the audio signal. So you're only going to hear the audio signal if it detects the audio signal, and you won't hear the audio signal when it doesn't detect the audio signal. But this detector is not arranged to just detect radar. So it's not telling you how strong the radar signal is, it's telling you how strong the audio signal is.
I'm now going to close one transmitter, put my hand in front, and you think about what will be the reduction of intensity of the sound here.
Alright, so understand, these are the two emitters. So you have, this is supposed to duplicate the double slit. And this is your receiver. It's going to be moved to different positions to see where the the interference pattern is. But just understand, these are audio signals that are on top of these radar signals, and this is not going to be detecting the radar. It's going to be detecting the what happens to the audio signals.
If I close one, substantially down, you may think that it is down by a factor of 2, because we have only one transmitter instead of 2. You're wrong. If you think that, you do not understand interference. It is
So, okay, so you see this. He says you do not understand interference. It has nothing to do with interference. It has to do with the fact that the audio signal, okay, is an amplitude modulation. It's AM, as he pointed out, which means the signal is made. If this was going to be, if this is called the signal, this is the 0 point. The signal is this. This is a peak signal. So this would be plus, say, 5 volts, and this would be minus 5 volts. So it's going through the whole cycle, through 0 to negative. So this is what's the signal's going, like this. It's a voltage signal. So that's what the audio signal is in terms of its amplitude. Now you can understand when that's off phase, when the two are no longer singing the same song, and this one, the one source, and this, here's the second source, let's say, and the second source is one wavelength off. You can see it's all the way down when this one's all the way up. And then vice versa. It goes all the way up when this one's all the way down. And so that's plus 5 volts, minus 5 volts is 0 volts. So the two audio signals are canceling out. Now, the 4 times just comes into the fact that when you, the signal all by itself would just be this plus signal. So when you're going into the negative territory, that means it's going to be 4 times weaker. So that's the 4 times part he's talking about here. So why does it decrease by 4 times when he covers just one of them? Is because when there's 2 of them, this signal goes twice as high. So it goes to 10 volts here and 10 volts down here when they're on phase. So when they're on the same phase, it's 10 volts and 10 volts. So that's the 4 times difference. So when you go back to the regular one, the signal, the total signal is 20 here, and it's only total signal difference is 20 and this is 10, but it's still 5 is the peak amplitude of the 1. The loudest it gets without the negative signal is still 5. So it's the 5 to 20 ratio that's the important ratio. The point you can see is that this would be counted as a 1, this would be 2, this would be 3, this would be 4. So you're just counting peakage. So there's 4 times as much peakage when the two are in phase, and then there's, you know, versus what 1 ohm's capable of producing at any one time, which is just 5 volts. Okay, I think I said that alright-ish.
And lower when I hold my hands over 1.
I mean, this just proves that he knows it's the audio signal that's getting fucked. He knows that's what's getting messed up by this experiment. The voltage signal, the signal on the radar, not the radar signal. The radar signal isn't getting messed up at all. The audio signal is getting messed up.
Figure it out for yourself. I'll test you in the final to see whether you really understood that. So now the sound is 4 times larger than when I cover one up. I'll cover the other one up. It's down by a factor of 4. I can cover this one up and then you hear nothing, of course. Now I will move this one to the location where there is destructive interference, which should be about half or 15.6 centimeters. Maybe you have good ears, but I hear nothing anymore.
Right. Now, so his claim is that this radar signal isn't making any radar here. And that's not true. The radar is going right in there, this thing's receiving the radar, and the only thing that's happening is that the 2 sound waves are now out of phase, and they're destructively interfering in the sense that it's you know, plus 5 volts minus 5 volts equals 0. So it's receiving no amplitude modulation. There's no amplitude to the modulated signal because one side was sending of negative 5 volts and one side was sending a plus 5. So this one ends up, because this one's closer, you can see that, the line of sight, and this one's a further distance. So the longer distance means this one gets out of phase to this one. And so when the 2 signals get here, one of them's going high, at the same time the other one's going low, and that always just equals a 0. The 2 cancel out. It has nothing to do with wave interference. Nothing.
Now I go through it and find the maximum, which is about 15.6 centimeters. Here it is.
So now they're 1 wave out of phase. So that all just means that now the 2 signals have caught up with each other in the sense that the 1 signal is now 1 complete wave out of phase, which puts them back on phase. So it's just that this wave is matching this wave in time. These, you know, this one was sent later than the other one, but because of the distance differences being so dramatic, the second wave from this one is getting there the same time as the first wave from this one, and the waves match now. So now they're constructively adding to each other. So it's 5 volts plus 5 volts and minus 5 volts plus minus 5 volts.
And the other side, here's the maximum at center. So here should be a minimum. There it is. And I go to the other side, there should be a maximum. And there it is. So what I have shown you today
is chicanery. It's just plain, you know, exaggeration, distortion, to validate a fundamentally unproven theory.
Is I've shown you the interference pattern of sound, of water, of red laser light, of radar.
Okay, so again, he's saying the radar interfered with the radar. That didn't happen in that experiment. It's just wrong to say it, and you shouldn't do that.
And at the very least, I hope I've convinced you as Young convinced the world in 1801.
Right, now so he's bringing up Young again. Young's crappy as crap experiment. Couldn't be a crappier experiment. Meant absolutely nothing. Compared to Newton's rings, okay, that happened 200 years earlier, Young's experiment is all meaningless. You have to be a physicist who didn't know what Newton's rings are to find Young's experiment remarkable or confusing. Because you already knew that a single aperture, okay, a single aperture created a pattern. You already knew a single aperture did that. Why would it be mysterious that a double aperture would create a bar pattern? Why would this be remarkable at all? Why would this Young observation be at all remarkable to a physicist who knew that Newton 200 years earlier had already done the experiment and had famously, it's been called Newton's rings. Again, Newton's rings are just the two-slit pattern in a circle. It's just the single slit in a circle. You just cut the bars here, cut the top off and the bottom off, and you got the same thing, the same pattern as the single slit experiment. And why is that experiment is so much more remarkable than two slits doing it? One slit doing it is much more remarkable than two slits doing it. So again, every time somebody brings up Young, it means they don't understand the history of physics. Because Young's experiment means nothing in the context of the chain of understanding. Newton already knew about it.
That light are waves.
Which is wrong. Feynman would say, no, that's not true. I don't think he's ever mentioned Feynman in any of these lectures. But anyway, no, see, but he wants to prove it. He wants to make it seem like, see how certain it is? Look, I just did this with radar and proved it with even radars showing you this wave interference. No, it isn't. You cheated the experiment.
And that means that Huygens was right and Newton was wrong.
No, Newton wasn't wrong about anything. Newton wasn't giving you explanations for anything. Newton speculated that it seems like they have to be particles, and he had his reasoning for why it seems it has to be particles. To say he was wrong about something is just crap. He didn't sit there and make any declarations about how this is how it happens. It can be no other explanation. He didn't do any such thing. He speculated, oh look, if I'm going to say what I think happens, this is what I'll say I'll think.
Now that should perhaps not surprise you, because Huygens was Dutch.
Right, and if a black man said that, you know, it's just who cares? But he's always obsessed because he's Dutch. He's always obsessed with always pointing out whatever Dutch scientist does something, he's always got to point it out that he's Dutch, which is just kind of unscientific mush. But Huygens was a great clockmaker, but his whole stupid wave nonsensey zillions, infinite number of wavelet crap is just crap. There's absolutely no evidence that any of that crap happens. So that was the end of the lecture. So we ended the lecture again using that experiment as a centerpiece for an argument that it's wave interference, and the experiment he did doesn't demonstrate anything about waves interfering. It has no waves interfering in it at all. It has two modulated signals. It has two converted into electrical signals that are interfering with each other as you change the phase of the receiving signal, of the receiver. So when you change the distance the signals have to travel, you change the phase of their, like I said, it'd be like my audio. If you had my audio coming out of two speakers, and you could, you know, if we made the distance dramatic enough, you could understand that if one speaker was 50 feet away and one speaker was 5 feet away, well, let's say 500 feet away, you'd understand that that one would be echoing what this one was saying. And it's the same effect when you're talking about the fact that the radar signal is only 3 centimeters long. The frequency between the ons and the offs. Alright, so I think that's enough. But this was just wrong. And I don't know how to interpret it, like I said. I mean, how do you interpret mistakes? Because you could say, okay, he just made a mistake. But to think he just made a mistake would mean he would have to not understand, you know, what happens when you put a signal on top of the radar. And that's the signal that's getting interfered with. I mean, to think that he really doesn't understand that that experiment did not demonstrate how the radar signal canceled out to nothing. Because the radar signal didn't. Trust me. Okay, if he really just detected the radar, okay, just detected to see if he could get a 10 gigahertz signal, the detector would have said yes, 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 all the way across. There would have been no destructive interference. Alright, anyway, enough said. It's MIT. Shouldn't be teaching that.